Why starting torque of a DC series motor is higher than a DC shunt motor? Let us consider first a DC shunt motor. When a DC voltage is applied to a DC shunt motor, field current IF flows in field winding, which produces flux. Current IA also flows in an armature conductor. Flux interacts with armature current to produce torque T. Torque is proportional to flux into armature current. In a DC shunt motor, flux is almost constant. Therefore, torque is proportional to armature current. In a DC series motor, field current is same as that of armature current IA. Torque is proportional to flux into armature current. Flux is proportional to field current, that is armature current. Hence, torque is proportional to armature current square. In a DC series motor, torque is proportional to armature current square, whereas in a DC shunt motor, torque is proportional to armature current. Thus, torque is much higher in a DC series motor than a DC shunt motor. During starting, back EMF is zero. Hence, armature current is very high. Flux is also very high. Thus, in a DC series motor, a very high starting torque is produced. DC series motors are used in cranes or hoists, where a very high starting torque is required. How tan delta is measured by a Schering bridge? Let us consider an AC bridge. Z1 is unknown impedance which is to be found. Z4 is a variable impedance. D is a current detector. Z4 is varied till current detector D shows zero current. Current I1 flowing through Z1 and Z2 is same. Similarly, current I2 flowing through Z3 and Z4 is same. Current in detector 0 means that voltage across detector is 0. That is, voltage across Z1 and Z3 is equal. Hence, I1 Z1 is equal to I2 Z3 or I1 by I2 is equal to Z3 by Z1. Similarly, voltage across Z2 and Z4 is equal. That is, I1 Z2 is equal to I2 Z4 or I1 by I2 is equal to Z4 by Z2. Thus, I1 by I2 is equal to Z3 by Z1 is equal to Z4 by Z2 or Z2 Z3 is equal to Z1 Z4. When current in detector is 0, we say that the bridge is balanced. Schering bridge is an AC bridge used to measure tan delta of insulation. C1 and R1 are capacitance and resistance of insulation to be measured. C4 and R4 are variable capacitance and resistance. These are varied to balance the bridge. That is, these are varied till current in detector D is 0. Z1 is equal to R1 plus 1 by j omega C1. Z2 is equal to R2. Z3 equals to 1 by j omega C3. 1 by Z4 is equal to 1 by R4 plus 1 divided by 1 by j omega C4 is equals to 1 by R4 plus j omega C4. Z4 is equals to 1 divided by 1 by R4 plus j omega C4 is equals to R4 divided by 1 plus j omega C4 R4. In a balanced bridge, Z1 Z4 is equals to Z2 Z3. That is R1 plus 1 by j omega C1 multiplied by R4 divided by 1 plus j omega C4 R4 is equals to R2 multiplied by 1 by j omega C3. R1 plus 1 by j omega C1 R4 is equals to R2 divided by j omega C3 multiplied by 1 plus j omega C4 R4. That is R1 R4 minus J R4 divided by omega C1 is equals to minus J R2 by omega C3 plus C4 R4 R2 by C3. Equating real and imaginary terms, we get R1 is equals to C4 R2 by C3, C1 is equal to R4 C3 by R2. Thus, capacitance and resistance of insulation are obtained. These are independent of omega, that is frequency. Tan delta is obtained as follows. Let U is the voltage applied on insulation. IC is the capacitive current flowing in the insulation. IR is the resistive current flowing in the insulation. Active power loss P is equal to UIR. Reactive power Q is equal to UIC. Tan delta is equal to P by Q is equal to IR by IC is equal to U by ZR divided by U by ZC is equal to ZC by ZR is equal to 1 by j omega C1 divided by R1 is equal to 1 by j omega C1 R1. What is the relation between electrical output power versus load angle in synchronous generator? Relation between electrical power output versus load angle is given below. P is equal to 3 EV sine delta by XS, where P is electrical output power, E is EMF induced per phase, V is terminal voltage per phase, delta is load angle between E and V, XS is synchronous reactance of generator. Load angle increases and decreases with load. Rotor flux phi r leads induced EMF by 90 degrees. Stator flux phi s leads terminal voltage by 90 degrees. The angle between phi r and phi s is also delta. When a generator is synchronized with grid, stator flux phi s rotates at synchronous speed and its speed is constant. When load on generator increases, rotor flux phi r and EMF E advances to increase load angle. How oscillations are produced in a synchronous generator? Oscillations means to and fro motion around equilibrium. Phi r is a rotor flux. Phi s is a stator flux. Delta is a load angle, that is angle between stator flux and rotor flux. Output electrical power P is given by P is equal to 3 EV sine delta by XS. That is, P is proportional to sine delta or Sin delta is proportional to P. When output power of generator increases, load angle increases. However, due to inertia, it overshoots the new equilibrium. Output electrical power has become greater than mechanical input power. There is retardation and rotor flux returns back. However, due to inertia, it again overshoots the new equilibrium. Output electrical power has become less than mechanical input power. There is acceleration and load angle increases, but it again overshoots equilibrium. Rotor flux keeps on oscillating till it returns to a new load angle. Since axis of rotor poles is same as that of rotor flux, they also oscillate with rotor flux. Rotor poles settle at new equilibrium position and make new load angle delta with stator flux phi s. What is meant by static unbalance in electrical machine? Unbalance in electrical machine is mainly of three types: static unbalance, couple unbalance, dynamic unbalance. Static unbalance is covered in this video. Static unbalance means that unbalance is in a single plane. When rotor runs, unbalance makes one rotation. Vibrations in both bearings are equal in magnitude and are in phase. Principal axis means axis which passes through center of mass. In static unbalance, principal axis is parallel to axis of rotation. Static unbalance can be corrected statically, that is, without running the rotor. Rotor is placed on knife edges. Unbalance comes down due to gravity. Balancing weight is put opposite to unbalance. In case provision is not there to put balancing weight in the center of core, two smaller balancing weights are put at the end of the core.